All right. Bismillahirrahmanirrahim. So this is what this is the summary of what we did last time in our discussion of camera models. So we were looking at the internals of this 3 by 4 matrix, which represents the camera. Okay. Um, in fact, I didn't mention this, but the specific camera that we have discussed, which is the pinhole camera, has the condition. It's also called a finite projective camera. I won't go into the detail of why we call it a finite projective camera. But it has the condition that this first 3 by 3 block of P should be non-singular. It should be invertible. Okay, that's what it turns out for a pinhole camera. So, but the pinhole camera is a 3 by 4 matrix, and in general, any camera, if I include the category of non-finite cameras, in general, any camera will be any arbitrary 3 by 4 matrix. But this particular one has the condition that the first 3 by 3 block should be non-singular, which means I should be able to take its inverse. Okay. Now in this camera. We looked at the internals of this and we realized that there are lots of inferences, that there are lots of parameters that we can extract from this 3 by 4 matrix. For example, this is the point at infinity along the x-axis, the image of the point at infinity along the direction of x-axis of the world. This is the same thing on the y-axis direction and the same thing on the z-axis direction, and this is the image of the world origin. Then we saw that this is the principal plane, and this is the axis plane, which is the join of the camera center C and the x-axis, and this is the join of camera center C and the y-axis. We also saw that the first three elements of this last vector, written as R3 vector, is the principal axis. Remember, this is a 3 vector, but it's a vector in R3 because the principal axis is an R3 vector, not an R2 vector. Okay, and we can take this 3 by 3 block and multiply that with the principal axis to get the principal point. Because the way we proved this is because we went to the point at infinity along the principal axis direction and then imaged it, and we realized that only the first 3 by 3 block is relevant there. We also saw that this first 3 by 3 block can be used to extract R and K by RQ decomposition, and once I have K, I can also read the principal point from K as well as the focal length parameters from R. And finally, the whole matrix, the null vector of that is the camera center. Yes, question.
MATLAB only gives us the QR decomposition. So how can we derive RQ decomposition?
Yeah, okay, that's a good question. In MATLAB, there's only a function of QR decomposition, which is really the opposite of that. So I can post a routine for RQ decomposition, which actually uses QR decomposition, but a bunch of transposes before and afterwards to get into RQ decomposition. You know that transpose changes the order here, so it's possible to take the QR routine and build an RQ routine from that. You can Google that also, you'll find MATLAB code to do that, but I can also post that. Okay. Any other question about this? All right. So because now we understand the camera, let's spend a bit of time to understand the action of camera on points and lines. Okay. I remember when we talked about primitives, we talked about points, lines, and planes, points and lines in 2D, and then we also talked about points and planes in 3D. Okay. So we are going to derive a bunch of relationships about how does the camera act on points and how does it act on lines and planes, really, because we'll see that lines are tied to planes in a sense in the camera. Okay, so that's the main topic for today, and I'm going to do a bunch of proofs here, really just using the mathematics that we understand here, and this is the type of work in which it's really beneficial that we are writing the camera in the projective mathematics way, because each of these proofs will be much more difficult if you were doing it in the normal Euclidean way. Okay, all right, so we already understand what is the action of camera on points. The action of camera on points is given by a point in 3 space is this cap x. Let me get my, yeah, so a point in 3 space is this cap x. I've kind of figured out how to, this is my achievement for today, I've figured out how to quickly switch my pointer because Last lecture I had lots of difficulty with that. Okay, so this is the point in 3 space. It's in P3. It's a 4-dimensional vector. Okay, and K is your intrinsic matrix, which is a 3 by 3 matrix. R is a rotation matrix, which is an orthonormal matrix of determinant plus 1. And then we have C tilde here. I write tilde here because it's a 3 vector, but I'm representing an R3 entity here rather than an R2 rather than a P2 entity. Okay, so this is the camera center. This is in general. But in the canonical coordinate system, by canonical view I mean the canonical coordinate system, which is the coordinate system fixed on the camera. Okay, so if I use that system, then the relationship becomes simpler. This extrinsic transform, R and C, the extrinsic parameters, which was really a rigid body transform of the camera, that disappears because the coordinate system is now fixed on the camera in the canonical configuration, and so that's just identity I pipe 0. Those are identity elements for rotation and translation. This 0, by the way, is written in boldface, which means it's a vector of zeros of appropriate size, in this case 3. And so I have only K and X, which are the terms here. Okay, so this is now familiar to us. We understand this pretty well. Okay, I want to a little bit formally talk about the notion of vanishing points now, because we have alluded to them many times, but I want to kind of formally see what they are. So because I want to derive a relationship for vanishing points in terms of image entities. Okay, so this is your camera. I have camera center C here, and this is my image plane, which we have now taken the convention that we always draw in front of the camera. In front of the camera center. The distance here is the focal length. Okay, all right. So consider a line in the world. Consider a line in the world. Okay, and there are some points on it. So let's say that this point is x1, this point is x2, this point is x3, this point is x4. Okay, these are points in 3 space. Let's just say along the carpet here there were these points. Okay, and the camera is looking at them. In a general configuration. Okay, so where is the image going to be of x1? How do I compute that? I have to, yes, very good. So I have to join x1 to the camera center and figure out where the intersection is going to be of that point. And similarly for x2 and x3 and x4, if I do that, this is what's going to happen. So that means that x1 will be imaged at this location, x2 will be imaged here, x3 will be imaged here, and x4 will be imaged here. Right? Now notice that these points are equal distance in the world, right? This distance is the same as this distance. They are equal distance in the world, but they are not equal distance in the image. They seem to be converging, okay, which is something we are familiar with. That's how cameras act on things which change the distance from the camera. So since x1 is closer to the camera than x2, and x3 is even further away and x4 is even further away, so that distance, that equal distance between them, maps to a smaller distance as I go further, because the thing is further away. Okay, so the question that I can ask is that there will be another point x5 here. Let's say these are like electricity poles or light poles along a road, and I took a picture of that. Okay, so there is like a lot of them. Okay, so but you notice that they are getting closer and closer. So the notion of vanishing point is that point at which they will get infinitesimally close, which means that this distance, what I've drawn in red here, this distance actually maps to 0. That, because it's decreasing, eventually it will decrease down to 0 or something very, very close to 0. And then in the limit that it becomes 0, that point is the vanishing point. Okay, for this direction. For this line direction, that point is the vanishing point. Okay, is that notion clear? Okay, so we want to be able to compute that. Okay, so my claim is, let's see if everyone agrees with that. My claim is that if I draw a ray D from the camera center, which is actually parallel to this line, then the point where that ray intersects the imaging plane is the vanishing point. Okay, everyone understands my claim? My claim is, you saw that these were getting closer and closer together. Okay, And so we have reason to believe that there will be some finite point beyond which they will not continue. Okay, uh, uh, even though in general in mathematics those functions which continue to decrease doesn't really mean that they won't go till infinity, but in this case there is a finite point beyond which this will not increase. Okay, and my claim is that to be able to compute that point, I can find the ray which is parallel to this line, their direction in the world. Okay, and I find the intersection of that ray at this point, and that point is the vanishing point. Anyone who can argue that yes, this is indeed a good claim, I mean, do you see a reason for that? Exactly, exactly. So as I go, the next point is x5 and x6 and x7. So I say, where is x infinity? And x infinity is going to be infinitely far away along this direction, right? But that's exactly where this ray will meet that ray, because these are parallel rays, so they'll meet at infinity. So both of them, so x infinity I can say lies on both this direction and this direction. In fact, x infinity is something that depends only on direction and not on the absolute position of this ray. Remember when we talked about ideal points, we said ideal points are parameterized only by their direction. Every direction has a different ideal point, but same directions have the same ideal point. So both these rays have the same x infinity. Okay, so I took my camera center and made a ray out of that which was parallel to this, because I know that that ray will also have the same vanishing point, and then I intersect that and I find that point, and I say these points which are getting closer will continue to get closer till they reach this, and then all points beyond that will map to this point, and that is the vanishing point. Okay, is that okay? So what does the vanishing point really depend on? It depends on the 3D direction in which you are moving, like the light poles. So if I find that 3D direction, I should know the vanishing point. Okay, and let's write that mathematically. So what is v? V is the image of x infinity. So how do you take the image? You just pre-multiply by p, which is a 3x4 matrix representing your camera. So v is really p times x infinity, which is, how do I write x infinity? Well, I could write it in this ray, or I could write it on this ray, and this ray has a direction d given by a 3 vector. So if I say d0, that's really x infinity, because I took the direction and appended that with the fourth element being 0. That means I've just gone to point at infinity in that direction. We did the same thing when we were trying to find the principal point. We took the direction of the principal axis and just appended a 0 to that, because that throws me at infinity, and then I can image it with p. Okay, so v is really this is really the beauty of projective mathematics. You can do these operations very simply without resorting to limits and solving those limits. Okay, so v is really p times d0, because that's x infinity, and that means that, well, p is really ki0 if I'm in the canonical view. All right, and so this 0 will multiply with this column, and so that really doesn't matter, and d will multiply by I, so I times d is d, so I'm just left with v is equal to kt. Okay, so remember, d is a vector direction in 3 space, but it's a vector measured in the camera canonical coordinate system. That's why I was able to use k is equal to I pi d. Agreed? So you give me a direction, and I know I've calibrated my camera. I know the focal length of the camera and the principal point of the camera and so on. I know k. So you give me a direction in the world as measured in my camera coordinate system, and I can immediately tell you the vanishing point. For those people who are working on self-driving cars and those types of things, you see lane markers along the road. If you can find the vector of those lane markers in the camera view, in the camera coordinate system, you immediately know where your horizon is going to be, because the horizon line is where that lane marker is going to go to infinity. Okay, which is a very important calculation for the sort of problems that you guys work on. All right, so to say this in text, the vanishing point of lines in direction d in 3 space is the intersection v of the image plane, which is the ray through the camera center, in the direction d. Okay, and this is given by v is equal to kd. All right. Here I've drawn an illustration. This is actually not a real photograph. It's a drawing, but it's a drawing done according to rules of perspective. So this is how you draw these poles. They are all equal distances, and those distances are actually computed by taking a point from the vanishing point and joining this point to that line. I mean, finding that intersection and then figuring out where the next pole is going to be. So you see their distances are decreasing, and if I know this direction in my camera coordinate system, if I can find this vector d in my camera coordinate system, then I can immediately just multiply that by k, and I will the answer will be this point. All right. Any confusion here or any questions? All right. We talked about action of camera on points. Let's talk about action of camera on lines. By action of camera on points, I mean you give me a point in 3 space, I can tell you where the image is going to be in 2 space, and I can also tell you the vanishing point if you give me a direction in 3 space. What's the action of camera on lines? Okay, so my claim here is that a line in 3 space will project to a line in image. This is actually the fundamental property of these pinhole cameras. Okay, lines map to lines. A line in 3 space will map to a line in 2 space. This is actually easy to see intuitively. Why? Because this is the geometric proof of that. So this is a line in 3 space, line L. I use capital letters for 3 space and small letters for 2 space. Okay, so there is a line L in 3 space, which will be a 4-dimensional vector, right? Well, no, let me take that back. There's a line L in 3 space. We did not actually discuss representation of lines. We discussed representation of planes. Okay, even though today we will write lines in their parametric form, so I'll discuss that. But fundamentally, a 4-vector in 3 space is a plane or a point. They are dual to each other. Okay. So however I represent it, let me call that cap L, whichever representation there is. This is a line in 3 space. Now consider 2 points along this line. You will know that they will join here. Okay. In fact, a line and a point. So to define a plane, you either need 3. To define a plane uniquely, you either need 3 non-collinear points, or a line and a point which is not on the plane, which is not on that line. Okay, that also defines a plane. So this line L and this point C, which is the camera center, defines a plane. Okay, which is this plane given by pi. And so this is one plane, and the image plane is another plane. So the image plane, 2 planes will intersect along a line. Okay, and so that line L, small l, is going to be the image of this line L. And so that's a proof, a geometric proof, that a line cap L will map to a line small l, because the line cap L will actually define a plane through the camera center, and that plane will intersect the imaging plane along a line. Okay, I want to, because this is a fundamental property of these cameras. In fact, this is like the fundamental property. This is the thing that the camera preserves. Remember, we talked about invariants of different transformations. So the invariant of this pinhole camera is that lines remain lines, straight lines remain straight lines. So it's a fundamental property. So I also want to prove it algebraically, just by algebra, right? Mathematics. So I consider 2 points, cap A and cap B, in 3 space. Okay, let's say this was A and this was B. Their join is the line. Okay, so the line formed by their join can be parameterized as. So I want to spend a little bit of time here on just understanding this. How do you parameterize a line? Because this is how we are going to write lines as far as this course is concerned, even though there are some other representations that people use, but we are just going to use this parametric form. Remember, if I was doing normal Cartesian mathematics on the Euclidean plane, even in 2D I can write, if I have a point A and a point B, okay, and I want to write a line between them, well, I can find that from their coordinates as y is equal to mx plus c, or ax plus by plus c is equal to 0. I can do all of that. But one other way to write that is that I can say that line is given by let's say lambda times a plus 1 minus lambda times b. Okay, by doing lambda a plus 1 minus lambda b, where lambda is a number between 0 to 1, I can move in between these 2 points. Okay, let's say lambda is 0.5. So what will happen? I have 0.5a plus 0.5b, which will be the point right in the middle, right? And if lambda is 2.25, I'm 0.25 closer to a and 0.75 closer to b, so I'll be somewhere here, right? So I can parameterize the points between these 2 points by choosing a lambda between 0 and 1, and then I can go beyond 0 and 1, and I can move outside the 2 endpoints of the line also. Okay, if lambda is exactly 0, then I am at b, and if lambda is exactly 1, then I'm at a, right? So this is like a parametric form of a line. Lambda is like a knob. You turn this knob and you will move along the line. All right. Now I can do the same thing in projective mathematics also. Think that a and b are projective entities, vectors in P2 or vectors in P3, and so I can do the same thing. I can write, let's say, lambda a plus 1 minus lambda b is a point along the line formed by the join of a and b. Except I can do something more, because the scale factor does not matter in projective vectors. Okay, so what I can do is, let's say I can divide the whole thing by lambda. That's still the same point. It really does not change. And if I divide the whole thing by lambda, I can cross this out and I can call this lambda prime if I want to. And so in projective mathematics, I can just say a plus lambda b is a parameterization of the line, is the parametric form of the line. Okay, which is what I'm doing here, a plus mu b. Okay, so if I'm given 2 points a and b, and I can write the line as x mu is equal to a plus mu b. I plug in different values of mu and I'll get different x's which are all along the line. Okay, so now I know how to represent that line in 3 space. I can take its image. Well, taking an image means just multiply by p here, px mu, which is what I'm doing here, p times a plus mu b, and I can expand this operation, so that's pa plus mu pb, and that's going to be the image point. And if I call PA as small a and PB as small b, then it's a plus mu b, which is also a line, but in 2 space now. So that's an algebraic proof that a line will map to a line. The reason I just did this 2 proofs is to be a little bit more clear about this, because it's a very fundamental property of the camera. Also, the field of projective mathematics has these both traditions. If you look at textbooks of projective mathematics, there are books written from the geometric standpoint, and there are books written from the algebraic standpoint. And they have proofs of the same things, the same theorems and so on. But in one book, all those theorems are proved by geometry, and in another book, all the proofs are done by algebra. So it's a tradition in mathematics that projective mathematics has developed both from the algebraic standpoint as well as from the geometric standpoint.
So further elaborate how you scaled and eliminated the lambda?
I said here that lambda a plus 1 minus lambda b is a point along the line formed by the join of a and b, right? So I can call that's x lambda, some point along the line. Okay, but x lambda, because these are projective entities, these are 2 projective vectors, so x is also a projective vector, which means the scale factor of it doesn't matter. So I can just multiply the whole thing by lambda and it will still remain x lambda. So if or divide the whole thing by lambda and it will still remain x lambda. So if I divide by lambda here and divide by lambda here, then this scale factor will cancel. It's still the same point x. This scale factor will cancel, and this will be just one scale parameter. Let me call that mu or beta or lambda prime or something. Right. So in projective mathematics, I can therefore write a line in its parametric form like this. Yes. No, it can't be a plus b. There is a ratio in which a and b are being added, so that ratio will not be eliminated, right? A plus b means you are adding them in equal weight. But as you move along the line, you have to, as you move closer and closer to b, you have to give more weight to b with respect to a. I'm saying the relative scale of them doesn't matter, but I mean, the overall scale of them doesn't matter, but the relative scale of them does indeed matter, right? Yeah.
So lines are perpendicular to the imaging plane. Those lines map to a point.
Yes, that's true. That's true.
How does your proof want to do that? Since you're talking about lines.
That's an interesting question. Lines which map to okay, so a line which is perpendicular to the imaging plane. I said there are 2 points A and B, which the gray plane is joined by is the join of the line and the point C, or of 2 points along that line and the point C, right? So in this case, what will happen is that A and B will be like this, which means that that the 3 points which I am joining become collinear, and then that doesn't define a plane, that defines a line. So it's the degenerate case of a plane. Okay, so then this proof will not hold because there is an assumption here that the point C, if I'm using line and a point, then point should not be on the line, but in that case it is. And if I'm using 3 points, then those 3 points should not be collinear, but they are in that case. So that's the degenerate case of plane collapsing onto a line and then that line collapsing onto a point.
So what would be the position of a line parallel
To A plus mu B. Okay, so A is A, B, C, let's say 1. Okay. Now B is, let's say, D, E, F, 1. Okay. Now the vector between A and B is actually given by B minus A. Okay. Which will be, let me just do that in R3. Okay, so B minus A is D minus A, E minus B, and F minus C. And now anything where the first two terms are the same but F minus C can be different is something parallel to this vector, to this line. Okay. In general, if I let me write a line directly rather than make a line from the subtraction of 2 points. So in general, in 2 space, if I write a line as ABC, then another line L prime, which is ABC prime, is parallel to ABC, is parallel to L, because A and B are the same, which is what defines the slope. Okay. All right. Any other question? All right. So we understand that a line will map to a line. And in fact, we can compute that line also like I did. If it is written in its parametric form, I can just multiply that with a p and I'll get the 2-space line. Let me talk about, so far I've talked about how point will map to an image. A 3-space point will map to a 2-space point in an image, and a 3-space line will map to a 2-space line in the image. I've talked about that. Let me talk about the opposite of that, which we call back projection. If you're given something in the image, how will you compute what it is in the world? Okay, so we call this back projection because a point will not uniquely map back to a point, it will actually map to a ray, right? Because all the points along that ray actually map to the same point in the camera. So given a point in the camera, you can only find a ray in the world uniquely, unless you have some other assumptions at play. Okay, so we call this back projection. Okay, so given a point x, now this is a small x. What happened? My whole finesse of switching my, okay, good. Given a point x, and I'm writing a small x here, so this is an image point. In an image of a camera with a camera matrix P, we want to determine a set of points in the world that map to this point. Okay, because the mapping is not unique as I go backwards, so I'm saying I want to find that set of points. That is, there will be a long array in the world that this point back projects to. Let me draw the figure. So this is your camera center. You are given a point x here, so you want to say, how do I compute this ray? It's supposed to be a straight line. Okay, So now note that the camera center C is always along that ray. To define the ray, what do I need? I actually need 2 points along that ray. Because if I have 2 points, then I can have the parametric form of that ray, just as I did on the previous slide A and B. Okay, so I'm looking for my guess of what are the 2 points on this ray that I know. Okay, now one of them surely is C. That is the definition of a pinhole camera. Every ray that enters the pinhole camera has to pass through C. Okay, so this one point C is common to all rays. In fact, it doesn't really depend on that small x. Okay, now if I can find another point, then I'll be done. Okay, if I can find a second point, then I would know the ray. That's what I'm after. Okay, all right. So my claim is that the point P plus X also lies along the ray, where P plus is by definition P transpose P, P transpose inverse. Okay, that's a mouthful. It's a big entity. This is actually in mathematics we call this the pseudo inverse. We have done one form of pseudo inverse, which was actually the inverse of this. The transpose was switched. That was A times A transpose A inverse. Okay. So one of them is called the left pseudo inverse and one of them is called the right pseudo inverse. So this is the other type of pseudo inverse. Okay, in fact, that pseudo inverse yields from solving an over constraint system. This is actually an under constraint system. I don't have a unique mapping here going backwards. Okay, so whatever this entity is, I just give you a name for this, but whatever this entity is, my claim is if you take this entity and multiply that with x, then that point is a 3D point which also lies along this ray. Okay, everyone understands my claim? Okay, I'm just saying P plus X, P plus times X is a point in the image, lies along the ray. It must lie along the ray, and where P plus has this definition. Okay, now I'm going to prove this. Yes.
So you effectively have taken a point when it's rated on 3D.
There is no 3D plane. Where's the 3D structure? No, I haven't. So I haven't uniquely identified that point. I'm just saying that there is some point along this ray. I don't know where it is. I'm not saying this particular point. I'm saying there's some point along this ray that has this definition. Okay, but I'm not doing a unique mapping of the small x to a large X because we can't do that. I can only do a mapping of a small x to a ray, which is a large X lambda maybe, which is parameterized by lambda. Okay, so let me prove this claim. My claim is that P plus X lies along the ray. Okay, so here's the proof. Where will the image of P plus X be? Well, I don't know where P plus X is, but it is some entity. So let me image it. How do I image something? I pre-multiply by P. So P times P plus X is the image of P plus X. Right? But what is P plus? I'll just substitute from this definition. So that means P times P transpose into P times P transpose inverse X. Right? But something times its inverse is identity, so that's just X. Okay? In fact, we really did this backwards. I mean, that's why we chose this entity to be like this, because we knew that this entity is such that if I multiply it with P, it will cancel out. So that's a really simple, elegant proof. Okay? So that's it. So therefore, P plus X must be along the ray. Okay? Just a note on dimensions here. Oh, I did a wrong font here. This should be an X like this. Okay? I'm using, I don't know if you realize this, but I'm using specific fonts and symbols to denote specific types of entities. Okay? All right. Let's do a just a check of dimensionality here. So what's the dimension of P transpose? What's the dimension of P? P is 3 by 4. So P transpose is 4 by 3 into what's P here? It's 3 by 4. And what's P transpose? That's 4 by 3. So by their multiplication, I get a 3 by 3 matrix. I take the inverse of that. That's another 3 by 3 matrix. And so I have a 4 by 3 multiplied by 3 by 3, which is a 4 by 3 entity. When I multiply that by X, a 4 by 3, okay, so so then that means that this whole entity is a 4 by 3 entity, right? Multiplied by a 3 by 1 here and a 3 by 4 here. Okay, so 3 by 4, 4 by 3, 3 by 1, that means the end result is a 3 by 1. Okay, which is an x direction. But this entity, sorry, I'm making a mess with my with my newfound tool, which is a pen. So this entity p plus x is really a 4 by 1 vector, which is a world point. Okay, because p plus is 4 by 3 and then x is 3 by 1, so it's a 4 by 1 entity. So all the dimensions work out here nicely. Okay, so I know one point along the ray, which is C, and I know the second point along the ray, which is one point along the ray, which is C, and I know the second point along the ray, which is P plus X. So that's all I wanted. I can write them in a parametric form now. So I can say all the points along that ray can be parameterized by lambda, which is P plus X, one point, and then lambda C, which is the second point. And I change lambda, I'll move along this ray. All right. So that's actually a very powerful result, because now I know how to back project a point onto a ray. Agreed? All right. Is there a question there in the end? ये जो आपके साथ बैठे हैं? Yeah. Do you have a question? Then please, Yani, if you have a question, ask in the class, right? Don't ask to the person next to you. Okay, so so I've said how to back project points into the rays in the general view, because I didn't put any restriction on P, so it can be in general K R I pi minus C tilde. But if I'm working in the canonical view, which means I'm working in the canonical coordinate system, this relationship becomes even more simpler. If I fix the axis onto my camera, then this relationship we'll see is even more simpler than what we have done, and it's useful to know that. Okay, so consider the back projected ray, which is I'll just call it in general the direction D. Okay, so I'll just call it the direction D. Because the back projected ray has a direction, so I'll call it D. Now all points along this ray can be written as the join of the camera center and the ray vector. Okay, so that's in general true. So it's 0, which is the camera center, plus lambda D. Why is it 0? Because I'm in the canonical view now, and in the canonical view, the camera center is at the origin. So really, if I've been careful, I should have written 0 tilde and D tilde, because I'm not writing them as 4 vectors, I'm writing them as 3 vectors. So x tilde, well, I put the tilde here, so at least that tells you that I'm working with 3 vectors. X tilde lambda is 0 plus lambda D, which is, well, it doesn't really, 0 doesn't really do anything, so it's just lambda D. Okay, so those are points along the back projected ray. The image of such a point in a canonical view will be, I can say the small x is k I pipe 0, because I'm in canonical view, I have I pipe 0 here, right? So x is k I pipe 0 times, I extend this to a 4 vector because I need to multiply with a 4 vector. So I can take any point along the ray really, and so I put this second element as 1. Okay, so it's lambda D1. Okay, and by changing lambda, I will move along the direction D, and so I can parameterize really all the points along that ray like this. Okay, and this will take their image, and the image will be at x because this ray was formed by x. All those points should map to x. Okay, but notice what is going on here. This one will multiply with this 0 here. Okay, so that really doesn't matter, and the lambda D part will multiply by the identity here, which will be lambda D, and so that really means that x is just equal to kd up to a scale factor. Sometimes people put like a dot here just to remember that this equality is up to a scale factor. That's why I dropped lambda, because I'm not really interested in the scale factor of x. All the scale factors mean the same thing. I'm not using this dot notation. Some books use that just to ensure that these are not mathematical equalities. These are equalities up to a scale factor. if that was the case, really I should go back and change all my equations and put a dot there, because they're all projective entities. So we have like in computing you can overload your operators. So we overloaded our equality operator to say that it's a up to a scale factor equality. Okay, so that just means that x is equal to kd, which is a very nice and simple relationship. If I want to find I'm given an x, I'm given my camera is calibrated, I'm given my k, I want to find that direction d in the world, I can just now invert this. I can say d is equal to k inverse x. Okay, which will be a 3 vector, because this is a 3 by 3 entity, this is a 3 by 1 entity, but this 3 vector is really a vector in R3. Okay, so that's a very straightforward relationship now. The previous relationship that I showed you, which was written as a parametric form of that ray, now it's a really straightforward relationship. The camera calibration matrix K relates the image point to a ray direction in the camera coordinate system. By camera coordinate system, I mean the canonical coordinate system. All right, which is a really straightforward relationship. In fact, this gives you some insight into the role of K also. Okay, think about your image, and you have a point in the image which you fixed in the pixel coordinates. Okay, which ray it's gonna map to in the world depends on K. And in fact, one of the critical entities in K is the focal length. So it depends on the focal length, which means that if I change the focal length, the ray direction for the same point will actually change. Okay, which is understandable, right? It's not I mean, because the only thing which is determining that direction other than that point is K. So if I fix X, I mean, it's really K which is determining the ray direction. And this kind of makes sense if you think about it, right? This is my camera center, and I have an imaging plane here. Okay, so this is going to be the ray direction. What if the focal length was longer than this, which means the imaging plane is here, but the point is the same, the pixel coordinate point is the same, then the ray direction is different. Okay, what if the imaging plane was here, then the ray direction is even less different. So it's actually the focal length and a bunch of other camera parameters which are included in K. I didn't say what's the role of the principal point and so on, but it's really K which determines where your rays are going to go in the world. Okay, yeah. Image what? Image compression? Yeah, okay, so we call this foreshortening effect, where remember I showed you in the beginning a picture of two people, but one was very far away from the other, and I saw that that person is much smaller than this person. Now, given some distance in the world, how small that person will appear is actually a function of focal length. You are very right of that. I wouldn't call it image compression, because image compression is the term we use for JPEG and H.264 and those types of algorithms, which reduce the size of the image file. But we call this the foreshortening effect. And how much foreshortening you will see is a function of the focal length. It's really the reason why if you want to photograph for your passport, right? So you go to a photographer studio. Now, what the photographer does is he takes you to a room, and in the room on one wall they have a chair, and he makes you sit there, and then he goes far away to the other wall, and from there he takes the photograph. Okay, now have you wondered why does the photographer waste so much space, right? Because he has to dedicate this room to take photograph. Why don't you just stand on the counter and he takes your photograph? Well, okay, one thing is lighting, you need good lighting and so on, but again, why have such a big room to do that? It could be like a really small setup and have all the right lighting there, and you could take your photograph. Okay, so the thing is, what the photographer does is he goes far away, and then he zooms into the view, and by zooming into the view, he increases the focal length of the view. The purpose there is to reduce this effect of foreshortening, because what will happen is that if you put the camera really close to the face, then the difference in distance, let's say, between the tip of your nose and let's say your ear is actually quite significant compared to the distance of the camera. Okay. which means there will be significant foreshortening between the tip of your nose and your ears. And in fact, because the nose is closer, it appears larger, and people don't like that. We figured that out, that people don't like that. Okay, your nose appears like larger than what it actually is. Why do people don't like that? We don't know. That's a human perception issue. but somehow there's this joke about. I mean, people joke about driving license photographs. They don't come out nice because often the camera is put too close to the subject, and it's a low focal length camera, and so your face appears distorted, the ears appear small, and the nose appear large, and people don't like it. In fact, it looks like you have a fat face somehow, right? Which somehow people don't like. So that's why the photographer, his business is to make money from photographs that that people like, and therefore he does this setup and zoom in and reduce this foreshortening effect.
Even mobile phones, we use them to take selfies. They are not from
Yeah. Okay. So if you okay, so mobile phones is an interesting, or all these commercial cameras are interesting. What the camera shows you often is not the reality. The cameras are engineered. There is a large signal processing pipeline inside the camera. What is the reality? The reality would be the raw sensor values that you get on your sensor. You just write them in a file and output that. None of the commercial cameras that you buy, like a DSLR from Nikon, for example, or your cell phone camera, none of the cameras does that. They do a bunch of processing steps before they churn out the image that you are able to see. In fact, if you buy a high-end SLR camera, like a Nikon camera, for example, they would allow you a RAW format and let's say a JPEG format image. And the RAW would be raw values that came on the sensor along with certain parameters of the processing pipeline. But what happens in that processing pipeline? Some things are pure blind signal processing. They try to improve the signal to noise ratio. They try to they will quantize the values. They will, for example, regenerate color because they don't have three different sensors to compute R, G, and B values. So they have a single sensor but a Bayer filter on top of it, where one pixel measures R and the next one measures green and the next one measures blue. It's like that. So from that they have to do interpolation to actually create the RGB values. So that happens inside the pipeline, and there are a bunch of other processing steps that are happening before the image is being churned out. But even after that, cameras realize that they will sell more. Camera manufacturers realize that they will sell more if you like the image that is being created. Okay, therefore they do some other corrections which distort reality. For example, they would try to make sky bluer than what it actually is, and they would try to make trees greener than what they actually are, because somehow people like that image. They say, wow, it's very nice. It's not how the world is, but it looks nicer, and then they would share it more and so on. Okay. Now cameras also have the capability to detect where the human is, face detection, using computer vision algorithms. They are built inside most cameras now, and they try to make skin tones better than what they actually are. So you don't look as nice as what your photographs comes out to be, but they try to do that. And because they can do face detection, and now they can fit 3D models onto that face, they can actually distort your face also to make it look thinner and so on. And you have these filters. These types of filters often are by choice, but you can make the face look thinner than that and make the eyes a bit bigger than what they really are. Some of the phones are calling it beautification filter. So you have a bar, you can select your beautification, right? It's all fake.
that's not the point. If you can include all this processing inside a small mobile phone,
Yeah.
why can't you do this in the photographer's camera, and then you can save the space and then take an image from the
The quality that you expect from I mean, I would venture a guess here. The quality that you expect from a passport photograph is different from the quality that a selfie might have, right? And so okay, that's one part of the answer. So the SLR cameras are trying to mimic reality in a better way. They still do color adjustments and so on, but they wouldn't distort the facial geometry, for example. Okay. Having said that, The new iPhone X, for example, has a 3D depth sensor on it. And that's actually an interesting topic. If you get a chance to discuss that, we might talk about what sort of algorithm goes into it, right? Into constructing that 3D. But what that happens is that not only does it have the image of your face, but it also has the whole 3D geometry of your face inside it, which means it can do really powerful stuff now with that face. For example, you can take a picture, and then after taking the picture, you can change lighting. You can say, how would my face look if I had a light source here? Well, to be able to compute that in graphics, I have to have the 3D structure, so I can compute the intersection, the dot product of the light ray and the surface normal, and that depends on what the shading will be, right? If the surface is oriented towards the light source, it should be brighter. If it is oriented away from the light source, it should be darker. So because they are computing 3D along with the photograph, they can actually do that manipulation after the photograph has been taken. And then they can do a bunch of other distortion manipulations also. So it's a really advanced sensor. It's actually more advanced than some of the SLR cameras that you get. Okay. All right. I didn't want to go into all this digression, but it's interesting you understand camera.
What is the difference between rays and lines and
They're really the same thing. Yeah. There's really not much of a difference. Yeah. Okay. So I talked about back projection of points. Okay. A point will back project to a ray. So let's talk about back projection of lines. Okay. So what do you think a line will back project to? A line should back project to a plane, really. Okay. So lines in image will back project to planes in the real world. So how do I find that plane? If you give me a line in the image, how do I find the equation of the plane that it back projects to? Okay, so here's my claim. The set of points in the world mapping to the line L, which is really the set of points on that plane, via the camera matrix P, is the plane given by P transpose L. Okay, first thing, check the dimension here. What is P transpose dimension? 4 by 3. What is dimension of L? It's a line in the image, so it's 3 by 1. So 4 by 3, 3 by 1 is a 4 by 1, which indeed can be a plane. Okay, a 4 by 1 vector, a plane is represented by a 4 by 1 vector. So my claim is that this plane P transpose L, if I think of it as a plane, this is the plane that is formed by the back projection of line L in the camera P. Okay, all right, so let's now prove it. So here's the proof. A point X in the image lies on the line L in the image if and only if X transpose L is equal to 0, right? Agreed. Okay, now a world point X, cap X, maps to a point Px, small x is equal to Px, right? That's through the camera, the action of the camera P. Now it will lie on that line L also if X transpose L is equal to 0, which means instead of X, I can substitute this, because this is really what X is now, right? That's the image of the world point X. So that means, well, really it should have been Px whole transpose, because that's what small x is times L is equal to 0. That's what X transpose L means. But AB transpose, you understand, means B transpose A transpose. Okay, so X transpose P transpose L is equal to 0. Then that world point X, which is mapping to the small image point X, lies on the line L. Okay, the small point X actually lies on the line L because the line is in 3D, but this world point is mapping to that image point. Okay, now what does that mean? That means that now, since X transpose P transpose L is equal to 0, if I take P transpose L, which is a 4 vector, it has dimension, if I take that to be a plane, I know that X transpose times pi is equal to 0 if pi is a plane, right? So that means this must be the plane, because this is equal to 0. So if I assume that P transpose L represents a plane, it's a 4 vector, then X lies on the plane, on that plane, which is the back projection of that line, because all of those X's will map somewhere along this line. Hence that plane is given by P transpose L. Okay, is the argument clear? So very simple, elegant proof. Again, I'm showing you, I'm mentioning this elegance again and again, so you appreciate it, because this is the simplification in these are really one-line proofs now, right? And this is the simplification afforded by projective mathematics. Okay, hence the result is P transpose L is the plane which is the back projection of the line L. All right. So now if this is a plane, so here's a line L. Here's a line L, okay, in the image. This is the camera center C, and this is that plane. I could have like extended it here, right? It's going out in the world. That's the plane, the whole gray plane, right? This is what that line back projects to. It comes this way and that way, and C is going to lie on that plane, obviously, because that line, every point on that line is actually joined to C. So C definitely lies on that plane. Okay, now we try to figure out what's the normal of this plane. What's the relationship between the normal of this plane? Okay, so the result is this. An image line L defines a plane through the camera center with the normal direction. My claim is that's N equal to K transpose L. That's just a mistake. There shouldn't be this apostrophe here. I'll try to remove this when I upload the slides. Okay, so my claim is that this normal of that plane is given by K transpose L in the camera canonical system, if I'm working in the camera canonical coordinate system. Again, I've made a claim that I can directly find the plane normal of the which is the plane defined by the back projection of the line L. Okay, and that's just given by, the normal is given by K transpose L. So let me prove it. Okay, but this simple relationship is in the camera coordinate system, so which means N will be defined now. N will become a 3 vector, but it will be a vector in the coordinate system of the camera. Okay, so let me prove that. Points X on the line L back project to directions. If I take one point X, it will back project to D is equal to K inverse X. That's something we have already proved just before, so I'm just using that as a result. Okay, that's what a direction back projects to. Now, since these directions, so let's say there's a point X here, it will back project to this direction, but this direction, this ray lies on the plane definitely, because the plane is actually formed by the whole line back projection, and this is just one point on the line, so necessarily this ray lies on the plane. Okay, so if it lies on the plane, it's at 90 degrees to the plane normal. I'm interested in finding the plane normal, so I'm linking it to some property of the plane normal. So it's orthogonal to the plane normal. Okay, right? Because every ray on the plane is orthogonal to the plane normal, so this particular ray is also orthogonal to the plane normal, which means what? That D transpose N should be 0. That's the relationship between two vectors which are orthogonal. Okay, and now I can just substitute in D, so that means K inverse X transpose N should be 0, but AB transpose is B transpose A transpose, so X transpose K minus transpose N should be 0. And what does that mean? Since X lies on that line, then X transpose L is 0, so therefore X transpose this thing, so this thing must be the line. Okay, and that means L is minus K transpose N. These are all three entities of these are, this is a 3 vector, this is a 3 vector, this is a 3 by 3 matrix. I can invert this, so N is K transpose L. Okay, yeah. Okay, yeah, the question is, most of these equations are in the canonical view. Well, not all of them. I've derived some of them for non-canonical view, but in the canonical view the mathematics gets extremely simplified. So sometimes it is useful to assume that your camera is in the canonical view and then measure entities in the world according to that view. So for example, a direct application of this equation, okay, would be that if I draw a line in the image, I will get a normal in the plane of that plane from this equation, and that normal will be a 3 vector. It's an R3 entity, but I will assume that this normal is relative to my camera. Okay, So which means if the normal came out to be vertical parallel to y-axis, let's say it came out to be 0, 1, 0, that means this line was really passing through the middle of the image, through the principal point, and therefore the plane was actually the optical axis lay on the plane. Therefore the vector of that, which means the camera is actually the image plane and this vector are orthogonal, I mean parallel to each other. Okay, so I can actually find the tilt of the camera with respect to a line, I mean the plane that is formed by the line using this. Okay, so sometimes in a lot of mathematics it's actually useful to assume that you are working in the canonical system, but you can't always do that in every entity. You might have to do a rigid body transform before you can apply this. It depends on what application you are doing. Okay, one I think last thing that I want to prove, and then we'll summarize, is think about the vanishing line of a plane in the world. Okay, this is a very practical thing to do. Think about a self-driving car. You have a camera on the car. There's a ground plane, which is the road. You want to talk about the vanishing line of that ground plane. Okay, so the vanishing point line of a plane is the image of the line at infinity of that plane. Okay, infinitely far away you have to go to find that. The vanishing line of the plane depends only on the orientation of the plane and not on its absolute position. This is in general what happens with entities at infinity. When we talked about an ideal point, we said ideal point, even in P2, an ideal point depends only on the orientation in which you are moving and not on the absolute position. So an ideal point for this vector and this vector will both be the same. Right? Similarly, the vanishing line for this plane and let's say the roof plane will be the same, because the normal vector of both these planes is exactly the same. Both planes are in exactly the same orientation. They are parallel. So parallel things meet at infinity. So the line at infinity for this plane and that plane is going to be the same. Okay, so parallel planes have the same vanishing line, like parallel rays have the same vanishing point. It's an extension of the same fact. Okay, so if the camera calibration matrix K is known, then the scene plane vanishing line can be found in the camera canonical view system in a quite straightforward way. Okay, in your practical images for the ground plane, this line is the horizon. So what I'm saying is, if I know K, I can find horizon of the ground plane in a very straightforward way. Okay, in the canonical, and I'll do this in the canonical coordinate system. So the orientation of the plane having the vanishing line L is given by, so this is a ground plane here. This is a ground plane here. Okay, I'm plane pi. Did I switch or not? Yeah, so given by pi, and I want to find the vanishing. So you have a camera up here. Let's say mounted on your car or truck or somewhere. You want to find the vanishing line of this plane, which is the ground plane. Okay, now the claim is that the vanishing line of this and this line of the plane that we first talked about, if this line is the vanishing line, because this relationship that we derived between N and L holds for any line, so if I take that particular line, which is the horizon, the same relationship between the plane normal applies. Okay, so let's say the argument is this. Let's say this line is indeed the horizon in the image. You see it. Okay, so you mark it. Now, since you know a line, you can find this N. Okay, by this relationship we derived on the last slide. And this plane that you are actually interested in has the same N because it's parallel to this. Why? Because this plane will also have the same vanishing line, because the vanishing line is the image of a line at infinity, and the line at infinity of any parallel plane is the same. So since this plane has the same horizon line and that line has this N, so therefore the normal of this plane is the same as this N, which means I can use the same relationship. It's the same relationship which holds for any line. If I find any line, the back projected plane has this normal. If I find the vanishing line, the back projected plane has this normal also. Okay, so the vanishing line as a function of the plane normal, if the normal was given, I wanted to find the line, I can just invert this. So L is equal to K minus transpose N. Okay, This is actually a very, very interesting relationship, practically speaking. It's the sort of problems, again, that we have people here from the industry. They're working in a company that is making cameras for trucks and cars and so on. So the camera is mounted here. You want to, if you identify the horizon, you can find the ground plane normal. If you find the ground plane normal in the camera coordinate system, you can identify the horizon. Okay, and finding the ground plane normal really is a function of how tilted the camera is, because that's the only thing that the ground plane normal depends on. So if you mount your camera carefully and you can measure the tilt of the camera, let's say you have a gyro built inside the camera, so you know the tilt angle of the camera. That just means you know where your horizon is. In fact, if the camera is such that the optical axis is exactly parallel to this ground plane, then the horizon is going to pass exactly through the middle of the image. If you tilt it downwards, the horizon is going to go up. If you tilt it upwards, the horizon is going to go down. By how much? That depends. That is given by this equation. It actually depends on the focal length. Okay? So this is a very interesting, simple relationship, and I have found that a lot of people working in computer vision actually don't know this. So, so they do a lot of other stuff to try to extract this geometry, but it's a straightforward relationship. Okay, so summary. Action of camera on points, lines, and planes. So action of camera on points. A camera maps a world point x to an image point small x. In general, x is equal to kr minus r pipe c pipe minus rc times x, and in canonical view, it's ki pipe 0x. All right. The vanishing point along the direction d, this d is a vector defined in the camera coordinate frame. The canonical frame is given by v is equal to kd. Again, a very simple relationship. All you have to do is identify that direction. Given a picture, identify that direction in your camera coordinate system. If you can do that, you can just find the vanishing point directly. Or the converse of that, if you can identify the vanishing point, you can find the direction by inverting this k. Okay. A point x will back project to a ray given by x lambda is equal to p plus x plus lambda c in general, where what is p plus? It's defined as p transpose p, p transpose inverse. And in the canonical view, this relationship is even more simpler. It's d is equal to k inverse x. Okay. Action of camera on lines. Lines in the world will map to lines in an image. That's a fundamental property of the pinhole camera. A line L in an image will back project to a plane P transpose L. We saw that, where P is the camera matrix. Okay. The normal of the plane formed by back projecting this line to the plane P transpose L, the normal of that is given directly by K transpose L, which is in the camera coordinate system. And the vanishing line of a plane with a normal n in the camera canonical system is L is equal to K minus transpose N. I missed out one summary line here, which is that if you give me a 3D line, I can also find the 2D line just by applying P to it, which is straightforward. I did that in the algebraic proof. Okay, so I can have a forward projection of a line and a backward projection of a line. So I didn't write the forward projection here, but I should have. It's forward and backwards. All right. Any question? Okay, so what we are going to do next, inshallah, next week is we have talked about pinhole cameras as and this is all the discussion I wanted to do about pinhole cameras. There are some other very interesting fundamental relationships, but I've kind of tried to take, because this is an introductory course, I've taken like a pick of some of the things that I felt are really essential. So this completes our discussion of pinhole camera. But what I want to do next is I want to talk about another type of camera, which is called an orthographic camera, which is kind of some sort of approximation to a pinhole camera under certain circumstances. In fact, if you have a pinhole camera which is with an extremely long focal length, a really big lens, then that's the one. Focal length tending towards infinity is what an orthographic camera is. Okay. The reason to discuss orthographic cameras, well, in certain situations they pop up as naturally. But also in certain mathematical situations, we take them to be a simplification of the pinhole camera, and it simplifies your mathematics sometimes considerably. So sometimes in papers or in algorithms, people work with an orthographic camera rather than a pinhole camera. So once I cover that topic, this discussion of camera models will be complete, inshallah. All right. Any question? Fine. All right. Thank you. So we are done. We have a quiz today, so we'll stop for that.